Hello everyone, in this video we're going to talk about how to rationalize a denominator. Okay, so it says if there is a radical in the denominator of a fraction, multiply the fraction by a form of 1 to eliminate the radical from the denominator. Okay, so in a previous video we talked about how to simplify radicals. I'll put the card for that in the top right hand corner right now. And we said one of the stipulations, or one of the things we want to look out for when we're simplifying a radical expression, is that there is no radical in the denominator. So if there is, we have to get rid of it, we have to eliminate it. It's called rationalizing. So here's how we're going to do that. Let's think about it in terms of square roots and cube roots. So if we have the square root of a number, let's just say, for example, we have the square root of 5, okay, in the denominator. Now, if we have the square root of 1 or the square root of 4 or the square root of 9, then that's okay. Those are perfect squares. Those are going to cancel out, or those are going to eliminate the radical anyways. Well, if we have the square root of a non-perfect square, what can we multiply that radical by for the radical to go away? Well, if we have the square root of 5, we're going to multiply it by itself, because when we do that, this becomes the square root of 5 squared. And so now if we square root something and then turn around and square it, those are called inverse operations. So this is just equal to 5. So that's how we're going to get rid of the radical. But we can't just multiply a fraction by whatever we want, but we can multiply a fraction by a form of 1. It doesn't change the value of the fraction. So if we have a square root in our denominator, we're going to multiply the fraction by the exact square root that's in the denominator, but over itself. So for example, the one that we just did, the square root of 5, if we had the square root of 5 in our denominator, we would multiply the fraction by square root of 5 over square root of 5, and then we would simplify it from there. That's with square roots. Well, what if we have a cube root? Well, let's say, for example, we have the cube root of 9 in our denominator. Well, cube root of 9, that's not a perfect cube. So if we had the cube root of 8 or the cube root of 27, those will cancel, right? Because those are perfect cubes. So for the cube root, we don't want to multiply the cube root by itself, because if I do times the cube root of 9, this gives me the cube root of 81, and that's still not a perfect cube, so that didn't help me at all. So with cube roots, we need to think about it a little bit more carefully. We're trying to get to the next highest perfect cube. So if I have a cube root of 9, I know, hey, I could multiply that by 3 to get the cube root of 27, which is a perfect cube. So if I had the cube root of 9 in my denominator, I would multiply by the cube root of 3, because this would give me the cube root of 27, which is equal to 3, right? So it gets rid of my radical. So when we're working with cube roots, we got to think about it a little bit more carefully. So we'll look at an example of each of those, and then we're going to talk about, what if my denominator is an expression? What if there's addition or subtraction? That's called multiplying by a conjugate, so we'll get to that at the end of this video. So let's start off with these two examples. Example number 1, we have the square root of 2y squared divided by 3. First thing I'm going to do is separate this, and I'm going to say the square root of 2y squared divided by the square root of 3, okay? Now, I can go ahead and simplify the square root of y squared on the top, but I'll just go ahead and rationalize this denominator. So in order for us to get rid of the square root of 3, we need to multiply this entire fraction by square root of 3 divided by the square root of 3. Because when we do this, now when we multiply fractions, we just multiply straight across, right? And we saw at the beginning, square root of 5 times the square root of 5 canceled out. It just gave us 5. So our denominator now is going to be equal to 3. And now we can multiply our radicals in the numerator. So this is 3 times 2, so the square root of 6y squared. And now we can simplify, so we'll come down here, and this is the square root of 6 times the square root of y squared divided by 3. Okay, and now with square root of 6, we can't simplify that any further, and so let's look at the square root of y squared. So I'll put our final answer going this way, square root of 6 and y on the outside. Actually, let's do it this way. Let's say y square root of 6 over 3, okay? And that'd be our answer for number 1. Now let's take a look at number 2. We have 5 divided by the cube root of 4, okay? So we know that we need to multiply this by the cube root of something in order for us to get rid of that 4. So if we think about our perfect cubes, 8 is a perfect cube, right? So I can just multiply this by the cube root of 2. When I do that, the cube root of 4 times the cube root of 2, that's going to give me the cube root of 8, which I know simplifies to 2. Cube root of 8 is 2, right? 2 times 2 times 2. So now I look in the numerator and I just have 5 times the cube root of 2, and there's nothing else we can do with that. So I'm going to write that down here, 5 times the cube root of 2, and that would be our final answer. Okay, so that's how you rationalize the denominator when the denominator is not an expression involving addition or subtraction. Well, what if the denominator contains a sum or a difference? Well, to do that, we're going to multiply the fraction by what we call the conjugate of the denominator. Why does this work? What does it do? Let's take a look at an example. So let's say, for example, our denominator is the square root of 2 plus the square root of 7. So the conjugate is the same two numbers we have there, so square root of 2 and square root of 7, but the opposite operation. So since we had addition, we are going to do root 2 minus root 7. And if you remember back when we did some videos on factoring, this gives us what's called the sum and difference pattern. So I'll link that in the cards right now, but let's see what's going to happen. Essentially what we can do is FOIL what we have here. So if I put my two binomials in parentheses, and we could FOIL this, right? So we go first, okay, so that's going to give me square root of 2 times the square root of 2, which would be just 2, right? Square root of 2 times square root of 2. And we're going to go outer, so this would be minus the square root of 14, inner, so plus the square root of 14, and then last. And this is going to be square root of 7 times the negative square root of 7, so those square roots are going to cancel. And now look what we've done. We have 2 minus, and we have these two radicals in the middle that are going to cancel out, right? This is exactly what our sum and difference pattern tells us. So we end up with 2 minus 7, which is equal to negative 5. And that allowed us to get rid of those radicals, okay? So let's take a look at a couple examples. The first one we're going to do is 4 divided by square root of 3 plus 1. So we're going to multiply both the top and the bottom of the fraction by the square root of 3 minus 1. Square root of 3 minus 1, okay? So now once we FOIL this, right, we're going to do, notice what happened, right? Let's take a look back at this example, okay? We started with root 2 and root 7, and we ended with 2 minus 7, okay? So if we think back, now let's look at our example that we're doing. If we do first, right, that's square root of 3 times the square root of 3, so that's just going to be 3. And then we have outer, so negative 3, or root 3 times negative 1, so minus square root of 3. Inner plus square root of 3, 3. And then minus 1. So now we see our terms here in the middle, they're going to cancel out, right? So we're just left with, let's write it down here, 4 over square root of 3 plus 1 times, here's what we're multiplying by. And now our denominator is just 3 minus 1, right? Because those inner terms canceled out. And now what we can do is distribute the numerator. So this would be 4 times the square root of 3, and then 4 times 1, so minus 4. So now when we go to simplify these, we can just do 3 minus 1. So we're going to have 4 root 3 minus 4 over, and 3 minus 1 is 2. Okay, so now we have an ability to simplify this a little bit. So we can say this is equal to, because now we have 4 over 2, which would be 2 root 3. And we can also do this 4 divided by 2. So 2 root 3 minus 2, and that would be our final answer. All right, now for number 2, we have the square root of 10 divided by 7 minus root 2. So we're going to go ahead and multiply the top and bottom by 7 plus root 2. 7 plus root 2. And now let's simplify. So let's distribute on the top. Let's do, this would be 7 root 10 plus a square root of 20 divided by, and now this is like our sum and difference pattern. So it's like a squared minus b squared. So this is going to be 7 squared, so 49, and root 2 squared, so 2. So now let's bring it over here. So now we have 7 root 10 plus a square root of 20 divided by 47. And I'm looking at the radicals that we have. The square root of 20 can be simplified because 4 is a perfect square factor. So we could say 7 root 10 plus, and we could do 4 times 5. So we can pull out a 2, so 2 root 5, and divided by 47. Okay, so now examine your radicals. Square root of 10, no other perfect square factors other than 1, and same thing for square root of 5. So we're all good here as our final answer with 7 root 10 plus 2 root 5 over 47. Okay? And that is how you rationalize the denominator.